Yeah.
All right, so last time we were working on some practice problems. We were looking at this problem E. The question was to design a DFA that accepted the language a to the n such that n mod 3 is 1. Union a to the n such that n mod 5 is 1. So the brute force solution to this has 15 states because the least common multiple of 3 and 5 is 15. So that will uniquely give you a n mod 3, n mod 5 combination. You can make some of those states final, and that will be a DFA that solves this problem. The question is there a simpler DFA that solves this problem? And we were in the process of figuring this out. Did anyone get a chance to explore this? And if so, what did they find? No one was able to explore it?
Yes.
What's your guess?
So that's 7 states,
7 states?
but I'm not sure.
Okay.
I'm not confident enough.
We'd have to be able to go take the 15 state DFA and find indistinguishable states pairs to be able to pare them down and combine them at the end of that whole process to be able to be sure. So I'm actually, because I want to cover and get through some regular expression stuff by the end of today's class, I'm going to leave this for people to go discover. I can give you the answer.
Yes. How many rows of seats? Is it 7?
It's actually 15. There is no reduction from the 15 state DFA. So yes, I want you to be able to go show that, be able to go look at the pairs of states and determine whether or not you can basically prove that all of them are distinguishable. Every pair is distinguishable. So there's the solution. You can't actually reduce it from here. To be able to do the next few practice problems, we have to cover just a little bit more content that we haven't seen before. It's only a couple of slides. Where we ended last time with regular expressions is we looked at the set notation for this language. L of A star dot A plus B. And we just applied these sets of rules that allowed us to manipulate this algebraically like we would a math expression. And eventually you got a regular expression of languages that you could represent in set notation and then start to be able to describe the strings that were in that language. One thing to talk about that we haven't really talked about yet is precedence of complex expression. So in math, we know that you do parentheses and then you do exponents and then you do multiplication and division in a single pass, and then you do addition and subtraction in a single pass. So there are precedence levels because we need to be able to avoid ambiguity in our regular expressions. So we need some kind of precedence. The entire purpose of precedence is to remove ambiguity. If I did something like 1 plus 2 times 3, without a precedence, since depending on which you do first, you get a different answer. It's important to say that you always do the multiplication before the addition. And that tells you where parentheses need to go if you want to override that order of operations. And very similar for here, we'll have parentheses for overriding the order of operations. So the first thing we're going to do is, besides parentheses, because parentheses aren't their own precedence, they're overriding the precedence order. The first we will do is star closure, then concatenation, then union. Those are the 3 big things you can do in a regular expression. You can express star closure, you can express concatenation, you can express union. So the order we're gonna do them, star closure, concatenation, union. And as you hopefully all know in math, if you multiply two numbers together, the dot or star can be omitted and you just concatenate together, like AB stands for A times B in math. So just like this, the dot for concatenation may also be omitted. So if you just have something like R1, R2, that stands for R1 concatenated with R2 or R1 dot R2. So I want to have a few practice problems here, and then we'll tackle some additional practice problems on the additional practice problem set of slides. All right, so we have something here that is some R. We're going to have A plus B star A plus BB. So think about the language and set notation that this language denotes. So be able to write out the sequence of characters, a set of sentences or a set of strings that are in the language. Just like before, we can kind of break this up into a left-hand side and a right-hand side. I'm kind of gonna place that boundary right here. So we have a left-hand side and a right-hand side. So this is concatenation. So we want to put something from the left-hand side concatenated with something from the right-hand side. So we can come up with sets from here. We'll just make every possible tuple that we can of an element from this half and an element from this half. Smash them together, that'll give us one of the strings in the language. So let's start with the left-hand side. What can the left-hand side produce?
Any amount of A's and B's.
Any amount of A's and B's, including 0?
Yeah.
So we could have something like lambda, A, B, A, B, BA, BB, etc.
Mhm.
What could the right-hand side give us?
A or BB.
Yeah. A or BB. So now the idea is we're going to start iterating this list, and for every element of this list, we're gonna concatenate it with each element from this list. So lambda concatenated with A is A. Lambda concatenated with BB is BB. All right, we've done lambda. A concatenated with A gives us AA. A concatenated with BB gives us ABB. Starting with B, we don't yet have a BA in there, so we will put BA in there. B concatenated with BB. We finish B. And you can see how you can continue this process. If you ever have multiplicity, remember that's perfectly allowed. We just ignore it in set notation. So if you were writing a program that generated these strings, it would be okay for there to be some repetition. Or you may want to find the repetition and remove it, just so that you only see one copy of each string. But this process would continue, but that's how I would generate that language in set notation. Over here, that's the eraser. Questions on this? All right, so that is one type of question that you may be asked with regards to regular expressions, is given this expression, give me a list of a set of strings and show how you get that. Note there is no lambda in the answer because there's no way to generate the empty string from the concatenation of both of them. Here's another one. If you get a list of strings for this, start thinking about, is there a pattern to this list of strings? If so, how could I relay the information so I don't have to give you an infinite series? How could you describe the pattern of what's emerging in this sequence? So we're going to call this the left-hand side, and this the right-hand side. Now you could split this into three pieces. The third piece would just be that last B. It would be constant, consistent, always there. If there's only going to be a set of one thing, you can just combine it with the thing before it.
So anything that starts with an even number of A's ends with And odd number of B's.
Exactly. That would be a wonderful way of explaining this language. So we know that parentheses AA star just basically means that if there are any A's here, there are an even number of them. Is this will generate either lambda or AA or AA or AAA. The number of A's here is 0, 2, 4, 6, always even. On the right-hand side, we have B, 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 B. So we have 1, 3, 5, always odd. So if you were to describe this sequence in English, you'd want to say all strings that start with an even number of A's and end in an odd number of B's over the alphabet AB. Make sense? Questions for the intuition of one, how to get there, and then two, how to be able to go from the pattern that you see and generate something in English that describes it. You could also, of course, you need to then combine all of these. But note that we need some way of enumerating two infinite sets on the left-hand side and the right-hand side. So it's not like you can enumerate for everything on the left-hand side and go through everything on the right-hand side, because you will never finish. So you could do something like B, since we're doing the lambdas first. B, 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 dot, dot, dot. And that shows that this goes on, this process goes on forever. Move to the next one. A, B, A, B, B, B. And then you would have a dot, dot, dot for that. And then at the end of this, you would have a dot, 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 showing that this whole procedure also continues. And this is really ugly. It's really hard to ascertain exactly what this means. I feel like this table makes that significantly cleaner and easier to understand. But if you have something like this, you still need some way to describe the set. The most intuitive way to do that is, of course, describing it in English.
So would you want us to, could we just make the table, or do you want us to write it out like how you have it on the right side?
If this said, what language does it denote, then you need some way of precisely describing that language. The best way to describe the language actually is a regular expression, I find, because you can't really go too wrong with that. If we needed a particular set notation for that, then you would need either something like this or some English description of every element of the set. I don't think the table quite does it justice, because you need to show that you put all of these together with concatenation. If you found a way to describe that, then that's probably fine. The set contained, you'd have to say something like, let's say, this to me is much cleaner than this junk, because you can actually see what it is and what it's doing. So mathematically, you're stating that it is all concatenations of x1, x2, such that x1 is a member of the left-hand side set and x2 is a member of the right-hand side set. And this allows you to basically construct the table in set form, where there's only one ellipse. If there are two ellipses like this in a two-dimensional set, that is ugly. All right, so we get the set of all strings with an even number of A's followed by an odd number of B's. We can go the other way. Write a regular expression for the following informal set description over zeros and ones. So this is an informal set description, just like I kind of just produced. So the language is all strings W that are in the star closure of the alphabet, such that W has at least one pair of consecutive zeros. So now you're using regular expression. So your goal is to produce something like this or something like this that uses either star closure or concatenation or union. Those together make an expression that represents this language. Anyone have an answer? Let's start with the reasoning. Do you have an answer?
Maybe. You could do like the star closure of 0, union 1. And then 2 zeros. And then the star closure of 0, union 1 again.
That's exactly right. So we know we need to get these 2 zeros somewhere in the string. This 0 or 1 star or 0 union 1 star is basically saying there are any number of allowable 0 or 1s, 0 included. So this would generate the sequence lambda 0, 1, 0, 0, 0, 1, 1, 0, 1, 1 on forever, which basically says this is any number of zeros or ones. And you do the same thing on the right-hand side. And somewhere in the string is going to be a 0, 0. There may be another 0, 0 here. There may be another 0, 0 here. But somewhere in the string, there is this 0, 0 that we can match to this section, and whatever comes before or after is arbitrary or does not matter. We know it's already in the string, in the language, based on just this 0, 0 that appears here. Does that make sense to people? All right, that's how we would represent any number of zeros or ones. Exactly as we just mentioned. Do another one. Regular expression for exactly the same thing, except we're going to accept the exact opposite. There's no pair of consecutive zeros. So this is the complement of the previous language. Everything that would have been accepted by the prior language will now be rejected. Anything that would have been rejected by the prior language is now accepted. And there's no nice, easy notation for saying the complement of this language. Yes, you could draw a bar above it, but we can do a little bit better by not including a complement in it. How do we negate the last language? What's the intuition for this one? The intuition for the last one is somewhere in the string, there has to be a 0, 0, and before and after, whatever that is arbitrary. What is the logical intuition for this problem? How do you ensure a string has no consecutive zeros? You can do it with a single rule. Imagine writing code for parsing this string character by character. What single logical rule could you implement?
Last character couldn't be a 0.
That
If
would,
you're replacing a 0.
yeah. That would apply to one place in the string. What rule could we use that would apply to any position of the string? You can use the current position if you want to. Something like if the current position is,
The current position is a 0, it has to be followed by a 1.
yes. If the current position is a 0, then the next position must be a 1. So think about that logically and now try to put that into a regular expression.
Don't know if it's like allowed, but. Like where my head immediately goes, it's like. Is there a way to have like exclusive ors in statements and regular expressions or not?
So if you want to do an exclusive or, how could we construct an exclusive or? We want to pick one thing or another thing. That would allow you to do both. If you do a union, you could pick both. How do we make it an exclusive or? So we're thinking very logically, which is good. Yeah, that's it. It's a union. Start with a union. You can think of it this way. Wherever this 0 occurs, it must be immediately followed by a 1. What happens before that 0 is an arbitrary number of 1s. Right? It doesn't matter how many 1s appear before the 0. It just cannot be a 0 that appeared before that 0. So we know that whenever a 0 occurs, it must be immediately followed by a 1. So if there is a 0, there must be a 1 that follows it. So if we star closure this tells us there may be some number of 0s followed by 1s. And if we say something like 1 star, that'll tell us there can be any number of 1s that precede this 0, 1 star. How do we get there to be repetition of this potential 0 or this potential 0, 1?
You're allowed to have like a star within a star.
Yes,
So could you do 0, 1, 1 star, and then every.
Something like that. Does that recursive logic start to map to the recursion that you've done before, where now you can repeat this entire sequence any number of times? We know we want to accept lambda, so there has to be a star around whatever we do, so there can be 0 instances of it. But this just says, wherever there's a 0, somewhere, if there's a 0, it has a 1 right after it. Or it has a bunch of ones, it has a bunch of ones before it and a bunch of ones after it. Any number of ones before and after.
There could be a string ending with a 0 though.
Yes, that is the one thing we have not taken into consideration with this. So there is a potential 0 at the end of this. How do you deal with that?
Could you just put 0 star?
That would allow there to be multiple zeros at
Oh,
the
yeah.
end. Yeah, so we have to, it's either 1 0 or 0 zeros at the very end. So I have an incomplete answer here that is kind of this logic, utilizing this logic, and this basically gets us to the point where we are here. We don't have parentheses around the 0, 1 because it's actually not super necessary. We know that 0, 1 has to happen somewhere. And this star actually means that this whole thing doesn't even need to happen. So the parentheses here were actually, and the star is not needed. The simpler regular expression that does the same thing. But this is incomplete for the exact reasons mentioned, that we could end this with a 0. This forces us, if we're going to do this, to end the string with a 1. Which means that something like the string 110 is not possible to construct with this, but adheres to the language.
Could you concatenate onto the end the union of 0 and lambda?
The other part that we haven't considered is anything that consists of all ones. So yeah, you could have at the end 0 or lambda. It says this could end with nothing, or it could end with a 0. We know this subsection ends with a 1 and does not have to repeat. So that handles the first case. What about strings of all ones?
Can you not already make that with the like the first parentheses?
If we added this in parentheses
Yeah.
and put star, that could now handle saying there are 0 of these, but now you can make strings of any number of ones here. Yeah, that would work. So I didn't think this is an answer. It's not the answer that I have on the slide, but there are lots of regular expressions that are equivalent. There's nothing that says if you don't get exactly the answer that is posted, that it's wrong. Just go through the intuitive logic yourself to say, for sure, are these representing the same language? Because you may have a correct answer. So here's a potential answer. 1 star, 0, 1, 1 star, star, 0 or lambda, plus or union, 1 star, 0 or lambda. Perfectly reasonable. Some alternate reasoning is this L is just repetitions of the strings 1 and 0, 1, right? Those are the only substrings that can be in there. Does that reasoning make sense? You construct something with no consecutive zeros. We need to, if we were to think about pairs of, or I guess, yeah, pairs of characters, there could be 0, 1, 1, 0, or 1, 1. And you just repeat those, you just can't have a 0, 1 following a 1, 0. So you could factor all of this out to say, well, we're not going to allow the 1, 0. if that's the case, then we just have repetitions of these two substrings. So for instance, we give an example of something in the language, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. That's an example of a string that does not have consecutive zeros, and I think goes through every case that we might care about. So we can construct this by saying the 1 comes from here, the 1 comes from here, the 0, 1 comes from here, the 0, 1 comes from here, 1, 1, 1, 0, 1. Although if it's ended with a 0, we have no way to represent that. So we still need to tack on the concept of the optional 0 to the end of this logic. And that's what gets us to this reasoning, or to this expression. Any substring 1 or 0, 1 repeated, then with the additional tack of that could end in a 0. As long as the last thing we selected from in here is a 1, then that's guaranteed to be the case, because that's both cases in here end with a 1. So no, both answers are correct. And both had perfectly reasonable logic that led to their construction. If you have two answers, they must denote the same language. If they're equivalent, two different expressions, we can again have many expressions, just like there are many possible DFAs that represent the same language, there are many possible regular expressions that map to the same language. Questions on any of this construction or logic? So just like we did for DFAs, trying to figure out the actual mapping here, how many are there of everything for a particular regular expression? There is only one language it represents. For every regular language, there may only be one regular expression, or there may be a ton of them. In fact, there may be an infinite number of them. If we care about showing that for a particular regular expression, what is the language that does this, we could construct an NFA that also accepts that language. We can show this by generating an expression that generates all labels from an NFA. And we can see that as that NFA continues to grow and grow and grow and grow and grow, then we can construct the different representations of the regular expression from all possible accepting states of the NFA. And you could then use induction to show that you could continue to generate more and more and more of these, and they would still always map to strings in a language. I will not make you do that. There's this concept of a generalized transition graph that can help us with the concept of cycles. So this is one of the first advanced topics that are not super necessary for the class. I don't necessarily anticipate having time at the end of this quarter, considering I think this class is probably 2 quarters worth of content. An automata theory and a compilers kind of shoved into one. So if there's time at the end of the quarter, people can make notes of, this is interesting. I'd like to see what the algorithm would be like for coming up with a bunch of regular expressions for a particular language, or showing how to convert from an NFA into one or more regular expressions. It's not easy, but it's something we could look into. All right, so that's everything in the slide deck for regular expressions, but I want to go back to these practice problems because I have a few more of these for you in here. So the first one here, find a regular expression for the set a to the n, b to the m, where n is greater than or equal to 3 and m is odd. answer?
Yeah. You have 3 A's. Followed by an A star. And then a B. And then BB star.
So that, great. Any arguments for or against this potential regular expression?
That's what I wrote, but, can we also use the other closure, the plus and like drop an A?
So using a plus here
Yeah.
that says drop a single A and then just say A plus,
Yeah,
you could, that would be equivalent to A star, which is why that the positive closure of something isn't necessarily required. It's more of a shorthand for reducing one of the characters in one of these expressions. Whenever you have something like A plus, you can always represent it as this portion of the sequence where we have A star. That says there's at least one of them. So yes, you could. Other arguments for or against this? Do we buy it? This is correct. There's one of a few different correct things, because we could easily put the BB star around. That's what we just did, around the last two. Or sorry, it is around the first two. So you could easily do this, and you'll show that it is commutative. Whenever you have at least one B, you can put the optional B's before it or after it, does not matter. So that's perfectly allowed. It doesn't matter which one of these A's you repeat, you could put the star after any one of them. So already we have many possible regular expressions. All right, that's number 7. How about number 8? Same A to the N, B to the M, except that the sum of N and M must be odd. Sir, excellent. Let's give people 1 more minute. And then with the last minute of class, we will go over the answer for this. If the sum of N and M have to be odd, what does that mean about the construction of the number of A's and the number of B's in the string?
the number of A's and B's, one of them has to be even with the other.
Yes. So one needs to be even, the other needs to be odd. How could we represent that nicely with an expression? Let's put it this way. We know that the string starts with some number of A's and ends with some number of B's. What differs is this middle character. If this is always even, and this is always even, then the character that appears in the middle will be what makes one of these odd. And it could be either an A. If it's an A, it makes this odd. If it's a B, it makes this odd. But we know this middle character has to exist. We don't know how many there are here, it's just that it needs to be even. We don't know how many characters are here, we just know it needs to be even. So how do we represent that? How do we represent an even number of A's?
A star.
A star. How do we represent an even number of B's?
Even babies.
Same thing, BB star. And how do we represent some character that's either an A or a B?
Oh, A.
Do we have A star, A plus B, BB star? And I just find that intuition, being able to break the problem down into its components like that, that is a learned process just from doing lots of these and thinking about how can I construct this string in general? But being able to break a problem like this down into this form makes it so much easier to construct a regular expression for. So that is an answer to number 8. Are there more? Who knows? Go find them. But between now and Monday's class, you have homework to work on. And we'll come back at the start of Monday's class and we can start doing these 3 problems before we move on to new content. Have a good weekend, stay safe. If you would venture out in the weather. So venturing out in snow.
And those stuff.
Yes.
I don't ski, it's so sweet. Just probably rip sweet jumps and not get. See, it's much better. Really, not that bad, but there's some like weird stuff. I'm trying to figure out what I'm doing. Maybe never.
No.
Mean you had junior. It's good, no.
That sounds pretty cool.
Snow is different. The snow is way different. The snow is so different. I don't skateboard. I don't skateboard. Yes. Yes.
First time.
First time. I did it.